Alright, this is an attempt to try to explain resonance in a way that you guys can understand. I didn't cover it in the lecture, and I don't think I had a good video of it in the section. So I've had several questions about resonance. So we're going to start out with ozone. And ozone is O3, and it has no charge on it. So we want to first draw a structure, come up with a structure for ozone. So I'll look at it and I say, well, oxygen. I look at oxygen and locate it on the periodic table, and we'll see that oxygen will have 6 valence electrons. We can figure that out by just counting from the left-hand side of the periodic table over to where oxygen is, and we'll see it's 6. So it's 6 valence electrons, and that's where we need to start. We have 3 oxygens, and so we're going to have 18 electrons that we're working with. When we're drawing Lewis structures, we only deal with the valence electrons. When you have 3 of the same element in a compound, we'll start those out by saying it's going to be 1 central one and then 2 on each side. Things orient as far apart as they can from each other because lights repel, and that's just the fact of life. So you just need to know that. Alright, so we know that with this arrangement, we're going to have at least a bond in between each one of the oxygens. So we'll draw in bonds there. And notice what we just did. We drew in these bonds, and each one of those bonds is 2 electrons. So we have 4 electrons taken from our total, and now we have 14 electrons left. Now, we'll go ahead and fill the octet on the terminal atoms. So I'll put lone pairs, 2, 3, 4, 5, 6 lone pairs on these oxygens on the ends, and that gives us a total of 8. So each of those terminal oxygens has a completed octet. We'll count up those blue electrons I just drew in there, and there's 12 of them, so we have 2 electrons left over. Now this molecule does not have a charge on it, and so we need to figure out where are we going to put those last 2 electrons. And so we'll put them on the central oxygen, just like that. Now, here's where it gets a little tricky. So at this point, we put those on the central oxygen. Problem is, this oxygen only has 6 electrons at this point. So what that tells us is it needs 2 more electrons. Well, the way that those 2 more electrons come to that oxygen is through a resonance structure, where a pair of electrons from one of the oxygens will actually form a double bond. So we'll wind up with a pi bond here. And now the central oxygen has 8 electrons. Since this is now gone, you wind up with 8 electrons on that terminal oxygen. What this does is, let's get another color in here, is this changes some things. Because we drew the structure as linear, but this isn't a linear molecule. Well, let's get a better color. There we go. Maybe this green will show up. See, we have 1 electron region, 2 electron regions, 3 electron regions. Well, 3 regions on an atom is going to give us a trigonal planar orientation, or trigonal planar geometry. So I'm going to redraw the whole thing. I'll do it in purple. And we'll have our oxygen here with its lone pair of electrons. And we'll double bond that to another oxygen, which then only has 2 lone pairs. And then another oxygen, which has 3 lone pairs, just like that. Now that is a stable structure for ozone. Resonance says that you move electrons, but you don't move your atoms. So the only thing that will move with resonance is electrons. So we have a pair of electrons here that's going to move and create a double bond, but the oxygen in the center cannot have 10 electrons. Remember, it can only have 8. And so at the same time, this double bond breaks, and we wind up with a new structure, which is still the same structure, if you think about it flipping in space. And so we'll wind up with this instead. And the only thing that moved was electrons. So if we had radioactively labeled each of these oxygens so we could identify them, we would know that the oxygens stayed in the same place and only the double bond moved. Well, actually, only the pairs of electrons moved. So that is resonance. These are resonance structures with each other, and these are equivalent. So it doesn't matter whether it's oxygen A that has a double bond or oxygen C that has the double bond. We would know that those would be equivalent, and those are resonance structures. We want to move on from there, and I want to show you a more complicated one, but let me pause for a moment. Okay, so we're going to get a little bit more complicated with this because I think that that's the best way to do it. And we're going to go with the carbonate ion, because we need to see what happens when you have a charge on things. And that is CO3, and it has a 2- charge on it. So the whole thing overall has a 2- charge on this carbonate ion. So we need to count up how many electrons we have. Well, carbon gives us 4 electrons, oxygen gives us 6 electrons, and then we have a 2- charge, which will give us 2 electrons. Well, oxygen, each one gives us 6, so there's actually 3 oxygens total, so that's going to be 18. So when we add all this up, we'll get 4 plus 18 plus 2, which will give us 24 electrons that we're working with. Straight off the bat, we should realize that carbon is the least electronegative of these elements. So carbon's going to go in the center. And we know without a doubt that we have to at least have a bond to each oxygen. And I'm going to space these out evenly at the moment because they evenly repel each other. So we're going to pretend like this is a trigonal planar molecule as a result of this. In a moment we'll see if this is correct or not. So we've got our carbon there in the center. We have used, we'll see, 2, 4, 6 electrons, so we'll take away 6 over here, so we get 18 electrons that we're working with. Now each oxygen has to have an octet. So I'm going to draw 1, 2, 3, 4, 5, 6. 1, 2, 3, 4, 5, 6. And that goes with the shared pair from the bond. 3, 4, 5, 6. So now each oxygen has an octet, and if we do the math on that, we'll see that that uses up the rest of the 18 electrons, right? So we got no electrons left over. So we're kind of happy with that, except for one thing. Carbon only has 6 electrons. If you'll notice, carbon has 2, 4, 6 electrons, and that's it. Carbon is not happy with only 6. Carbon has to have 8. So just like we did with the ozone earlier, we are going to take a pair of electrons and we are going to create a double bond instead. That will satisfy the octet on carbon, and it will satisfy the octet on the oxygen also. So we'll wind up with a resonance. Well, it's not really resonance at this point. So we're going to have oxygen double bonded to carbon, oxygen, and oxygen. So trigonal planar was the correct geometry. 2 lone pairs on this oxygen, 3 lone pairs on these oxygens. Just like that. Okay, now it's important to realize that this lone pair, this bonding pair we have here with the double bond, we're going to have all kinds of resonance that takes place in this structure. The bond can move there, and we use another pair over here, so we get a resonance structure that is like this. 1, 2, 3, 4, 5, 6. 1, 2, 3, 4, 5, 6. And from that point, we can also have the pair of electrons moving there, and then a pair of electrons moving here. And so we'll wind up with this structure. Where well, I did a bad job of drawing that. Well, 3, 4, 5, 6. 1, 2, 3, 4. Just like that. So all of these are equivalent resonance structures. Now this is where we need to come in and talk about formal charge on this. Because we look at this and the entire molecule has a total charge of -2. And that's where the extra 2 electrons came from that helped us to fill those octets. Let me get a drink of water. Okay, I'm back. It's early in the morning, so you got that early morning congestion, you know. So we're looking at, we'll look at this resonance structure here. And we want to talk about the formal charge because each of these atoms has a charge on itself. And remember, we just said that carbonate as a whole, and I'll put a big bracket around it, is a 2- charge. So where would these negatives actually be held? Well, let's look at our structure and let's do some math and figure it out. So let's look at our carbon, and we're going to calculate the formal charge. Now the formal charge is going to be the number of valence electrons minus the number of non-bonding electrons, and then minus 1/2 of the number of bonding electrons. Alright, so the number of valence electrons minus the number of non-bonding electrons minus the 1/2 of the number of the shared electrons, or the bonding electrons. So we'll look at carbon, and we'll see that carbon starts out with, so we're looking at the formal charge on carbon, and carbon starts out with 4 valence electrons. We looked that up from the periodic table. Looking at the structure here, we see that there are no non-bonding electrons on the carbon, so that's going to be minus 0, and then we're going to take 1/2 of the bonding electrons, and we're going to subtract it. So we'll look at the number of bonding electrons. We have 2, 4, 6, 8. So we'll take 1/2 of 8, and so 4 minus 0 minus 1/2 of 8 is equal to 0, because 1/2 of 8 is 4. So that carbon has a formal charge of 0. Now I'm going to label the oxygen so we know which one is which. So we're going to name that A, B, and C, so that we can get make sure we do the charge on each one of them. So this first oxygen, let's say this is oxygen A. Oxygen starts out with 6 valence electrons. We looked that up on the periodic table. Now we're going to subtract by the number of non-bonding electrons. So we'll see 2, 4, 6 non-bonding electrons. So that's going to be 6 minus 6. And then we're going to subtract by 1/2 of the number of bonding electrons. And in this case, we got 2 in this one bond here. And so that's going to be 2. So 6 minus 6 is 0. Minus 1/2 of 2 is equal to a -1. So the formal charge on this oxygen is actually a -1 charge. So I'll put a little negative out there. It looks more like an equal sign. But I also don't have my glasses on. And then we'll say, here's the B oxygen, which we should be able to look at it and determine that, hey, it's going to have the same charge. But let's go through the steps anyways. Oxygen has 6 valence electrons. We're going to subtract the number of non-bonding, 1, 2, 3, 4, 5, 6 non-bonding electrons. And then we're going to take 1/2 of the number of bonding electrons. And there's a bond here, so that's 2 electrons. So we'll take 2, and so we're going to wind up with a formal charge on that oxygen of -1 also. So we've got another negative charge over here. That's our 2 negative charges that we get. So it should be able to predict from a process of elimination that oxygen C has a 0 formal charge. But let's do the math to make sure, because this is a teaching class. All right, so here was oxygen number C down here. 6 valence electrons. How many non-bonding electrons? 1, 2, 3, 4. So we're going to subtract out 4 from that. And then we're going to take 1/2 of the total of the bonding electrons. And we see we have 2 bonds. So that's 2, 4. So 1/2 of 4. And that is going to be equal to 6 minus 4 is 2. Minus 1/2 of 4. Half of 4 is 2. So 2 minus 2 is 0. So we have a 0 formal charge on the oxygen labeled C. And that's a formal charge. Now, let's go back up over here and let's see why this is not probable. I'm looking at the one we started out with before we said, hey, it's got to have a double bond. This is an actual resonance structure of it, but it's unstable. The reason it's unstable is because of formal charges. I mean, that's an easy way to determine it. Because we've got some formal charges we can calculate here. So let's look at our central carbon here. So carbon's formal charge, remember carbon starts out with 4, and then we're going to subtract, what do we subtract? The non-bonding electrons on carbon, and we'll see we have no non-bonding electrons on carbon. And then we're going to subtract from that the number of shared electrons, or 1/2 the number of the bonding electrons. And so we'll see here we have 2, 4, 6, right? So 1/2 of 6, and so we get 4 minus 3, so the charge on this carbon is actually a +1 charge, which is a possibility with this resonance structure. Now, if we'll do one of these oxygens, but all these oxygens are equivalent, So oxygen is 6 minus, and then we have 6 non-bonding on this one, and we have 1/2 of the number of the bonding electrons, which is 2, and that's going to wind up with a -1. So each oxygen, because these are all equivalent in this structure, has a negative charge. This is a resonance structure. It is an unstable resonance structure because this central carbon has a positive charge, and then in our other one, the central carbon has a neutral charge, a neutral formal charge. And also for this oxygen, it's also no charge here. So you have lower formal charges, makes it more stable. This carbon with a positive charge is called a carbocation. And while a carbocation that has a higher substitution like this one is more stable, I think that's right. I'll double check in a minute. This is not the favorite resonance structure for the carbonate ion. You may say, well, what about the charge of the total thing? Well, if you look at the total molecule, the total structure there, you'll see that we have 3 minuses, 1, 2, 3. So we got -3 plus the charge here on the carbon, which is a +1. And so it gives us an overall -2 charge. So see, nothing has changed. We've still got the right number of electrons. It's just our bonding is not correct because carbon wants to have a lower formal charge. And for completion's sake, I want to show you one more that is pretty common that we run across from time to time. You may have heard of it before. It's SO4 with a 2- charge, and this is the sulfate ion. Same thing here. We're going to draw this structure, and we're going to put the least electronegative, I said lowest, but same thing. The least electronegative atom is going to be in the middle. So sulfur is less electronegative than oxygen. If you don't know how to look at electronegativity, there's a website that I like that has a chart. It's called ptable.com, and they have a periodic table that specifically shows electronegativities. But you should know the trend is you get greater in electronegativity from left to right. Electronegativity increases, and it also increases as you go from bottom to top. So if they're on the same row, the one that's higher, etc., blah, blah, blah. Okay, so sulfur is going to be the least electronegative, so it goes in the center. I went ahead and drew it like it is. I should have gone ahead and shown you the electron counts, so we're going to do the electron counts too. Okay, so sulfur has the same electrons as oxygen. It has 6 electrons, and oxygen has 6 electrons, but there's 4 of them, so our total number of electrons is going to be, that's 24 plus 6, so it's going to be 30 electrons that we're working with. And this has an overall charge of -2. And so that's going to add 2 more electrons to it. So we get 32 electrons to work with. All right, so we're working with 32 electrons. Let's zoom that in a little bit here. We went ahead and drew our structure, so we can go ahead and we can take 8 electrons out of it. So we're going to take away 8 electrons. And 32 minus 8, I think, is 24. Sometimes, honestly, subtraction has always been my Achilles heel when it comes to math. Really good at everything else. It takes me a moment to subtract. I don't know why. All right, so we know we got 24 electrons. Let's go ahead and let's fill the octet on the oxygens, because the terminal atoms will have a completed octet. 1, 2, 3, 4, 5, 6. 1, 2, 3, 4, 5, 6. Just like that. Count those out. We got 6 for each oxygen, so that's a total of 24 electrons, and that gives us a 0 electrons left. Now, we may look at this and say, oh, well, that's good, but the problem with this compound is that we have a formal charge on everything. Each oxygen is going to have a minus charge on it. We did the calculation earlier with the carbonate, but let's go ahead and do the calculation anyway. So oxygen's formal charge is going to be equal to the total it brought in valence electrons minus the lone pair's electrons, and then subtract 1/2 of the bonding electrons, and it's 2 of them here, and so we get -1, but it's the exact same calculation from carbonate. So each oxygen would have a -1, and since we know that the overall charge on the whole thing is -2, that means that sulfur has to have a +2 charge. Well, it doesn't like to have a +2 charge because sulfur is even though it's less electronegative than oxygen, it is a electronegative element. So what happens is we form double bonds to satisfy this. And you may say, but wait, Mr. Hurt, if we form a double bond there, sulfur winds up with too many electrons. Remember, if it's in the 3rd energy level, with the 3rd period there, the 3rd row on the periodic table, or below, it can have an expanded octet. So sulfur does actually have an expanded octet. So when we move that over and we make a double bond instead, it actually reduces the charge. Formal charge on oxygen becomes 0, and the formal charge on the sulfur becomes just +1. Well, that's a step in the right direction. So let's do that again. And this is just a resonance structure of the first thing I drew. And so we form the double bond there. Well, the oxygen now has a formal charge of 0, and the sulfur's formal charge is going to be 0 also. So a more stable structure for this sulfate ion is going to have sulfur in the middle, single bonded to 2 of the oxygens, and double bonded to 2 of the other oxygens, to the 2 other oxygens. And that gives us the proper formal charges that we need. Okay, because now we just have a negative charge up here on this oxygen and a negative charge on this oxygen. You may say, well, that just doesn't make any sense. Well, it does. That's how it works. We can calculate the formal charge. Let's do it for the oxygen here on the bottom, the double bonded oxygen. So this oxygen has 6 electrons it starts out with. It has 4 valence. It has 4 non-bonded electrons now. And then we're going to subtract by 1/2 of the bonding electrons. And there's 4 bonding electrons. So we get 6 minus 4 is 2 minus 2. So we have a formal charge of 0 on that oxygen. Well, what about sulfur? With all that stuff going on, you got to be thinking, what's up with the sulfur? All right, sulfur brings in 6 electrons initially. We're going to subtract it by the number of lone pairs, which we have no lone pairs on this sulfur. And then we're going to subtract it by 1/2 of the bonding pairs. We'll look at our bonding pairs, and we'll have 2, 4, 6, 8, 10, 12. And so we get 6 minus 0 minus 1/2 of 12, which would be 0. So that tells us the formal charge is just like it is. Now that's one resonance structure for the sulfate ion. And it kind of goes without saying that at this point we're just moving electrons to show other resonance forms. So the bond will go there, and then we'll get a pair that comes here and makes the double bond in that location. And the same place goes around. So you can kind of start filling in the drew a C, I meant to put an S. So we would have a double bonded here. I'm going to leave off all of the electrons just for brevity, because this is getting long as it is. And so then another resonance structure would actually be oxygen with sulfur, and then oxygen there, and then double bonded to this oxygen, and then I drew a carbon again. I don't know what's up with me. Be like that, and then we could have this. So at this point, I'm not even looking at moving electrons around. I'm just looking at the pattern that we're taking. And you can see that all this stuff these are all equivalent resonance structures. Oh, forgot my double bond on that one. They are equivalent now. However, the one with single bonds that we started out with, where the formal charges were all messed up, that is also a valid resonance structure. It's just not very stable, and it's not likely to be seen. I hope that clears up your questions about resonance.